In fluid mechanics, there are many places where we use the derivative. Thus, in this lesson, I'm going to talk about how to define the derivative. The derivative was invented to describe things in the physical world. For example, speed is distance divided by time, and so if something travels 10 meters in 2 seconds, we say that the speed is 5 meters per second. And let's write this as an equation. We'll use v to represent the speed, and the amount of distance we'll use delta d, and the amount of time we'll use delta t like that. Now suppose we drop a rock and we want to know the speed right before it hits the ground. So it's sort of natural to do the following. We'll say the distance it's going to fall is right there, delta d, and we'll measure the time, delta t, and we'll plug into the formula and we'll get the speed. The problem with this is that this approach would be wrong, because what we would get in this case is we would get the average speed as the rock fell. It would actually be moving twice as fast as the average speed right before it hit the ground at this point. And Newton thought about this problem, and he said if we're going to really calculate speed, we have to use a little different formula. We have to take the distance traveled over an increment of time and take the limit as the time interval goes to 0. And so what Newton's idea was, instead of using this whole interval, let me switch colors here. Let's just take a different interval. So we'll use this as delta d prime, and delta t prime, and use this formula, and this will give us an accurate value of the speed right before the rock hits the ground. And this is the basic idea of the derivative. A change in variable 1 divided by a change in variable 2 in the limit as variable 2 goes to 0. In this basic idea we can generalize. So the generalization, if we have the derivative of any variable a with respect to variable b, this is defined as in the limit as the amount of b goes to 0, and we take an amount of a over an amount of b. And this is the definition of the derivative. So I like to think of the derivative as a ratio of an amount of a to an amount of b in the limit as the amount of b goes to 0. Now if you look in any calculus book, the derivative will be defined like this. The derivative of a function f with respect to x is defined as the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. And sometimes, instead of a delta x, a calculus book will use the symbol h here. And this definition here and the one I've shown you here are exactly the same thing. And now I'm going to show you how to make the connection. So we want to take this right-hand side here, and we'll write this as limit delta x goes to 0, and a function at x plus delta x minus a function at x, we can write that as the change in the dependent variable divided by the change in the independent variable. And if you look here, I've really written the same thing. It's a ratio in the limit as the quantity in the denominator goes to 0. The derivative of a function of f with respect to x is often described as the slope of the tangent line at the point of interest. And this is really the same idea we've been working on. because if we calculate the slope, we're going to do rise over run. So let's get that set up. And so the rise is this distance right here. And that's delta F. And the run is this distance right here, which is delta X. And so the slope is the amount or change in the dependent variable corresponding to the amount or change in the independent variable. In summary, the definition of the derivative in math books looks like this. And if you take it apart, the definition of the derivative of A with respect to B means the amount of A divided by the amount of B in the limit as the amount of B goes to 0. So the derivative is really describing a ratio when the quantity in the denominator is going to 0. And we'll use this idea to define many terms in fluid mechanics as well as to do many practical applications. We hope this lesson has been very useful. Thank you very much for listening.